So today we're going to start the chapter on Isaac Newton, chapter 7. But I just want to review Cardano's formula for solving the cubic. So Cardano's solution of the cubic equation. So suppose we have a polynomial. Let's see. I'll write down a polynomial. F of x is x cubed minus 3x squared plus 4x minus 12. And we want to solve the equation f of x equals 0. So step 1, compute the depressed cubic. A depressed cubic is a cubic where there's no quadratic term, there's no x squared term, there's just a cubic term, a linear term, and a constant. And how do you do that? If you have a general cubic, ax cubed plus bx squared plus cx plus d, you let x be y minus a over 3b. And when you make this substitution, you get a polynomial in y, which will have no square term. This will be depressed. So in this case, the leading coefficient, a, is equal to 1, b is minus 3, so we're going to let x be replaced by y minus 1 over 3. So let's make that substitution and see what we get. So we have a new polynomial, I'll call it g of y, which is what we get when we replace x by y minus a third. That's y minus a third cubed minus 3 y minus a third squared plus 4 times y minus a third minus 12. So to solve a cubic involves a lot of calculation. And there will be, certainly on the second exam, a cubic that you have to solve. So you need to work out a number of homework problems by hand completely. You have to know what to do. So we have to expand this cubic, right? Let me just remind you that if you have y minus something, say y minus p, and you cube it, this is y cubed. Sorry, is there a question? So you need to mute yourself if you are not already muted. So y minus p, when you cube it, this is a special case of the binomial theorem. You get y cubed minus 3py squared plus 3p squared y minus p cubed. So in this case, p is a third. So when you expand this first term, you get y cubed minus 3 times a third y squared plus 3 times a third squared y minus a third cubed. If you expand this by the binomial theorem, that's what you get. Minus 3 times this squared, y squared minus 2/3 y plus 1/9, plus this, 4y minus 4/3 minus 12. So the only thing to do is to simplify it and hope we don't make too many mistakes. Let's see. We get y cubed, this is this first term, minus y squared, 3 times the 9th plus 1/3 y minus 1/27 minus, oops, let's see, something is not right. What is not right here? Oh, it's the wrong substitution. Why did I make this substitution? It's not y minus 1/3. So this is wrong. Oh, I'm always glad when I make a mistake. It's great. So let's start again. If we have the general cubic, f of x equal ax cubed plus bx squared plus cx plus d, and I want to solve this equal to 0, what can I substitute for x to eliminate the quadratic term? So if I let x equal y minus, say, some quantity p, when I plug that in, f of y minus p is going to be a times y minus p cubed plus b times y minus p squared plus c times y minus p plus d equals 0. And when I expand this, I get a y cubed minus 3py squared plus some other terms. I only care about the quadratic terms. Here, when I expand this, I get b y squared and some other stuff plus other stuff. And this other stuff where the dots are either multiples of y or just constants. So this is ay cubed minus 3apy squared plus by squared plus other stuff. This is ay cubed plus, let's see, what do I have here? I have b minus 3ap times y squared and other stuff. And I want this to be 0. I want the quadratic term to disappear. So I want b minus 3ap to be equal to 0, or 3ap equals b, or I let p be b over 3a. Right. So that's going to be my substitution. X is y minus p, where p is b over 3a. So I started with the equation, the cubic, f of x equals x cubed minus 3x squared plus 4x minus 12. And in this equation, the leading coefficient, a, is 1, and the coefficient of x squared, b, is minus 3. So p is b over 3 times 1. P is minus 1. So my substitution is to let x equal y minus p. That's y minus minus 1, or y plus 1. So that's the correct substitution. So I hope you can follow this, but if not, it's all being recorded and you can study this when you're studying.
I have a question.
Yes, go ahead.
This is a different method from the one you chose to do the first attempt.
Oh, because the first was wrong.
Yeah, but this is a different way approach.
No. So I was trying to skip a step. So here was my first equation. And I said, let x equal y minus a third. Right? I said, make this substitution, and I made it, and I saw it doesn't work. It fails, because I made a mistake, because I was just trying to be quick. That was wrong. So I want to know, how did I make my mistake? The mistake is this is the wrong substitution. So I said, okay, I'll go back and figure out from the scratch what is the right substitution. So if this is your general cubic and you want to substitute x equal y minus some unknown quantity p to eliminate the square term, the x squared term, what does p have to be? So I plug in y minus p, and I see that p has to be equal to this. All right. So, and in this, and this is the equation I started with, so that I'm going back to it. In this equation, a is 1 and b is minus 3. So b over 3a is minus 1. So I'm letting x equal y minus 1 or y plus 1. So it's the same method I used in the beginning, except in the beginning, I made a mistake. Right? I'm not changing the method in any way. It's like you have a problem, you add 2 plus 3 and you write down 6, and you're going to get the wrong answer because you made a mistake. So you go back and you correct the mistake. Does that make sense?
Kind of.
Well, I mean,
Can you go back to the first one real quick?
the one that's wrong?
Yeah.
Okay.
You see how you have where is that? Y minus, where is that? Yes, let x equals y minus a over 3b.
Yeah, so this is wrong.
Oh, okay.
Because what is it supposed to be? Should be x equals y minus b over 3a. Right?
Oh, I see.
I just wrote it down the wrong thing.
Okay, okay.
Right? So don't look at that. Look at this. Right? Because that's what's right. So we can start again and try and do it correctly. So we have f of x, the cubic, is x cubed minus 3x squared plus 4x minus 12. And I want to let x equal y plus 1. So I'll end up with a polynomial in y, which is what you get when you replace x by y plus 1. So that's y plus 1 cubed minus 3y plus 1 squared plus 4y plus 1 minus 12. So you expand this and you hope the quadratic term, the square term, disappears. Y plus 1 cubed by the binomial theorem is y cubed plus 3y squared plus 3y plus 1 minus 3 times y plus 1 squared, that's y squared plus 2y plus 1, plus 4y plus 4 minus 12. So what do I get? I have y cubed. Here I have 3y squared. Here I have minus 3y squared. They cancel, which is exactly what I want. Here I have 3y minus 6y is minus 3y plus 4y plus, what's my constant? 1 minus 3 plus 4 minus 12. So this is y cubed minus 3y plus 4y plus y. This is 5 minus 15 is minus 10. So I get y cubed plus y minus 10 equals 0, or I have the reduced cubic, y cubed plus y equals 10.
That's negative. That was a 4 or 5.
Where?
Negative 3 plus 4 minus 12.
1 minus 3 plus 4 minus 12.
All right, I got it. Thanks.
So this is my reduced cubic. If you have the general form y cubed plus my equals n, so in this case, m equals 1, n equals 10. So we're going to let the solution will be y equals t minus u, where t is the cube root of n over 2 plus the square root of n squared over 4 plus m cubed over 27. Let's see. If m is 1 and n is 10, n squared over 4 plus m cubed over 27 is, let's see, this is 100 over 4, 25, plus 1 over 27. Well, whatever it is, that's what it is. Let's see. 25 times 27. This is 135, 54, 276. This is 200 and, sorry, that's not right. 606. This is 676 over 27. All right. 676. Trying to think whether that factors in some nice way. Okay, so t is equal to the cube root of n over 2, that's 5, plus the square root of 676 over 27. And u is the cube root of minus n over 2, plus that same square root. Minus n over 2 is minus 5, plus the square root of 676 over 27. So we get the answer. Y, we get y. Y is cube root of 5 plus the square root of 676 over 27 minus the cube root of minus 5 plus the square root of 676 over 27. And so that is the answer. That is exactly the answer. Now you might prefer that in terms that are more humanly understandable. So let me take my calculator or my computer and do a calculation. This number is, so here I have to use calculator or computer. At least I have to use that. So this is roughly 2.1547. And this is 0.1547. So we get, this is really, every decimal approximation, it's an approximation, is 2. So we get y equals 2. And but we want to find x, right? Because we want to find the solution of this equation. X is y plus 1. So x equal y plus 1 is 2 plus 1, or 3. So that says that 3 is a solution. So let's check. Remember, f of x is x cubed minus 3x squared plus 4x minus 12. So f of 3 is 3 cubed, 27, minus 3 times 9, plus 4 times 3 minus 12, and that's 0. So this is correct. So for my original polynomial, that was the original polynomial, Cardano's method gave us the solution, x equal 3. So this is solving the cubic, which it is very nice to know how to do. Any questions about that? So in solving the cubic, one thing you needed to know was how to expand something like a plus b cubed, right? I mean, if you have a plus b to the first power, that's a plus b. Of course, if you have a plus b to the 0th power, that's 1, because anything to the 0th power is 1. A plus b squared is a squared plus 2ab plus b squared. We needed to use that. And a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. So we needed to know all of these expansions to solve the cubic. And of course, in mathematics, when you see something like this, it's natural to ask, can you keep going? Like, what about a plus b to the 4th? So that turns out to be a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. I mean, you're going to have to know these things on the exam, and it's a lot to memorize, so I have to show you a way to get all these expansions without memorizing anything. But what's a plus b to the 5th? A to the 5th plus 5 a to the 4th b plus 10 a cubed b squared plus 10 a squared b cubed plus 5ab to the 4th plus b to the 5th. Huh, cool. Could I do another one? A plus b to the 6th. See, you notice in these expansions, you have a lot of terms in powers of a and b, but the sum of the powers, like here, a plus b to the 5th, the sum of the powers is 5. 5, 4 plus 1, 3 plus 2, 2 plus 3, 1 plus 4, 0 plus 5. When you expand a plus b to the 6th, you're going to get all the terms in a and b, powers of a and b, where the sum of the powers is 6. And the only question is, these are all possible, a to one power, b to another power, where the sum of the powers is 6, where the exponents are non-negative integers, 0, 1, 2, 3, up to 6. The only question is, what are the coefficients? So if I'm lucky, this is 6, this is 15, this is 20, this is 15, this is 6, and this is 1. You'll notice, by the way, if I look at just the coefficients, they're always symmetric. Like here, like I have 1. Here, 1. Here the coefficients are 1 and 1. Here the coefficients are 1, 2, 1. Here the coefficients are 1, 3, 3, 1. Here the coefficients are 1, 4, 6, 4, 1. You see, they're the same if you read from left to right or right to left. Here I have 1, 5, 10, 10, 5, 1. Here I have 1, 6, 15, 20, 15, 6, 1. So, in fact, I have this triangular array of numbers, which is called Pascal's triangle.
When do we originally learn that?
When was this discovered?
No, at what level of math do they talk about Pascal's triangle?
It depends on how good your high school math teachers are. All right. I mean, and where you went to high school, or maybe even middle school. For example, if you're from the Caribbean, you went to high school in the Caribbean, you will have learned this very early because the level of math instruction there is extremely high. They took the old British colonial system and kept it. They weakened it in England, but in large parts of the Caribbean, they still have the English system, which was at a very high level. In the U.S., in the U.S., education is decentralized. It's not just every state has its own rules, but even local school boards have their own rules. In a country like France, there's a national system. They say, I don't know if this is true, that if you go to any high school in France, on a given day, every high school in the whole country is teaching the same thing because they have like a curriculum set by the national government. In America, there's a huge variation. And even in New York City, it varies from school to school, and it depends in part on what your teacher wants to do. So a lot of students have seen this before college. A lot of students have not. A lot of students don't see it in college unless they're math majors maybe, or computer science or something. But yeah. So if you haven't seen it before, that's fine. Now you see it. Like there are lots of things in this. Like I was just talking to a kid. I don't know. He goes to school somewhere in New York. I mean, I'm talking to him on Zoom. He contacted me, and he was in. He's either like 10th grade or 11th grade, and he had seen Cardano's formula. It wasn't part of the curriculum. It was just that, when the teacher was teaching quadratic equations, the teacher happened to know the cubic equation formula and just showed it to the students. I think that's all it depends on. I can't, yeah. But this array of numbers is called Pascal's triangle, and it goes on forever. So you want to know, how do you get like from one row to the next? So you can see certain patterns. For example, the beginning and end of each row is always a 1, right? Like first term is a 1 and the last term is a 1. And there's always this symmetry. If you go from left to right or from right to left, you see the same numbers. But there's also another very important rule, which you see, and I was careful the way I wrote this down because I could have written the triangle in different ways. You can think of, like here, this is a 1. You can think of this as like infinite, actually infinitely many numbers, but just like wherever there's not a number to the left or the right, just think of zeros, right? If you want to. Each number in like the second row, 1 is 0 plus 1, 1 is 1 plus 0. Let's say, or let's say that the ends are always 1s. This 2 is the sum of the two numbers to the right and the left just above it. 3 is the sum of the two numbers just above it to the left and the right. And that pattern keeps going. Each number in each new row comes from adding the numbers just above it in the previous row. So suppose I want to find the 7th row. here I have the sixth row. The sixth row is 1, 6, 15, 20, 15, 6, 1. So this is row 6. And I want to get row 7. So row 7 is going to have one more. So this has 6, 7 numbers. Row 7 is going to have 8 numbers. So the ends are always going to be 1. The number that goes here, you take the sum of these two above it. That's 7. What's here, the sum of these above it, that'll be 21. What's here is the sum of those above it, 35. What's here is the sum of those above it, 35. What's here, the sum of the two above it is 21. What's here, the sum of the two above it is 7. And you'll see again, and this is because this row is symmetric from the left and the right, the new row is symmetric from the left and the right. And these numbers will be the coefficients when you expand a plus b to the 7th. So a plus b to the 7th will be a to the 7th plus 7, a to the 6th b, plus 21, a to the 5th b squared, plus 35, a to the 4th b cubed, plus 35, a cubed b to the 4th, plus 21, a squared b to the 5th, plus 7, a b to the 6th, plus 1 b to the 7th. So you can go back and forth from the row of Pascal's triangle to the coefficients when you expand a plus b to the 7th. Like, how do you get a plus b to the 8th? Well, you need to get the 8th row. Here's the 7th row. What will the 8th row be? It'll start and end with a 1, and then you just add like consecutive, like here, this will be 1 plus 7 or 8. This will be 7 plus 21, 28. 21 and 35 is 56. 35 and 35 is 70. 35 and 21 is 56. 21 and 7 is 28. 7 and 1 is 8. So this is now the 8th row of Pascal's triangle. And if you take a plus b to the 8th, this will be a to the 8th plus 8a to the 7th b plus 28 a to the 6th b squared plus 56 a to the 5th b cubed plus 70 a 4th b 4th plus 56 a cubed b to the 5th plus 28 a squared b to the 6th plus 8 a b to the 7th plus b to the 8th. Right? That's Pascal's triangle. Actually, not coincidentally, but in the chapter we're about to start, which is on work of Isaac Newton, the great theorem is not connected to, it's not the binomial theorem, but the great theorem, but the chapter does include a discussion of the binomial theorem. And let me see if you can see this. When I put it here, this is the book. And here is Pascal's triangle up to the 7th row. And here is the 8th row. Right? So this was known. So Isaac Newton lived in the 17th, beginning of the 18th century in England. What I'm doing was certainly known in India hundreds of years before this, but there wasn't much commerce between Asia and Europe at this time, and certainly not at an intellectual level, and this wasn't known. And I don't know exactly when Pascal's triangle, maybe it was due to Pascal, though I doubt it, I assume. Pascal did many things, but his name is not necessarily attached only to things that he did. But this is Pascal's triangle. And so we have let's say the binomial theorem, the first case at least, which is to expand a plus b to the power n for positive or non-negative integers n. So if you wanted to expand a plus b to the 13th power, how do you find how to do that? Well, one way, not the best, but one way is by expanding to the 13th power, you're going to have a to the 13th plus lots of terms. The general term will be a and b to powers that, like if a is to the k, b is to the 13 minus k. To b to the 13th. Times some coefficient, which is called the binomial coefficient. And you can find this, among other things, by using Pascal's triangle. Right? Now, if you wanted to find the coefficients for a plus b to the 13th, there's a lot of writing to do. You'd have to keep computing all of the rows of this triangle, getting longer and longer and longer until you get to the 13th row. Right? And so we'd like to find a more efficient way to compute the coefficients in the binomial theorem than using Pascal's triangle. Pascal's triangle is fine for small exponents, but if this were not a plus b to the 13th power, but a plus b to the 113th power, you don't want to have to compute over 100 rows of this triangle just to find out these 14 numbers. So what I want to work up to is what is called Newton's binomial theorem, where we expand a plus b to the n, but actually it's much more powerful than that. Suppose, for example, just make it easy. Instead of a and b, suppose it's like 1 plus x to the n. So if you let a equal 1 and b equal x, it's just a little bit simpler to write down. So 1 plus x to the n. Right? So like 1 plus x cubed is 1 plus 3x plus 3x squared plus x cubed. 1 plus x to the 4th is 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th, and so on. But Newton did something much more powerful than this. He said, suppose you have 1 plus x to the power n, but maybe n's not a positive integer or 0. Maybe n's a fraction, m over n. And maybe it's even negative. So this is what we're trying to look at now. Like, what are some examples? Suppose you want to expand the square root of 1 plus x. 1 plus x square root is 1 plus x to the power half. Right? Can we expand this somehow in powers of x? Could you write this as 1 plus something times x plus something times x squared and so forth? Or suppose we had something like 1 over 1 plus x cubed. This is also kind of a binomial. This is 1 plus x to the power minus 3. Because I remind you that in general, x to the minus k means 1 over x to the k. right? So a negative exponent means the reciprocal of x to the positive exponent, right? Can you write this as 1 plus something times x and so powers of x, right? Is this possible? Of course, in Calc 2, at the very end of the course, you learn about power series and Taylor series, and you get a way sometimes to do this, but that's much more powerful mathematics. You need a lot of calculus for this. Is there some purely algebraic way of solving something like this? And this is something that Newton did. And you know, when you're looking at the history of mathematics, in history they always tell you, no matter what kind of history, you know, history of the United States, they always say, go back and read the original documents. And the problem is that the original documents, no matter what language they're written in, English, Spanish, Portuguese, whatever, they're written in that language, but the way people wrote and the way they used words and symbols 200 years ago or 500 years ago is different from what's used today. So even if you know English and you're reading an old document in English, it's like almost like learning a new language in some sense. So in a letter from Newton to a German, Newton was British, Leibniz was German, and a contemporary and peer almost of Newton. Newton wrote this. This is what it looks like in the text. It's already translated into modern way of writing letters, but P plus PQ to the M over N. So this is almost, think of this as like 1 plus X to the fractional power is P to the M over N plus M over N AQ plus M minus N over 2N BQ plus M minus 2N over 3N CQ plus M minus 3N over 4N DQ plus ... Now, what in the world does this mean? So, I mean, if you look at these fractions, it's sort of like the M over N, like the denominators go up N, 2N, 3N, 4N, and so forth. The numerators are M, M minus N, M minus 2N, M minus 3N. This is P and this is Q, but what's not given here are what are A, B, C, D, and so on. So M over N is a positive or negative fraction. So if we can figure out a way to expand this, this is a great advance on what was previously known, because what was previously known was the binomial theorem just for positive integral exponents, not fractions and not negative numbers. And Newton is claiming that he can expand a binomial to any power, whether it's positive or negative, and whether it's a fraction or a whole number. So let's see. So I'm trying to see how much more than Newton, right? So let's say, suppose A is P to the M over N. If you let A be P to the M over N times Q, let's see, and B be, so this A is the previous term. Suppose B is the previous term, M over N AQ, which is M over N, and the previous term A, or A is P to the M over N times Q. C is going to be the previous term. So I have A, B, C is the previous term, M minus N over 2NBQ, which is M minus N over 2N times M over N P, the M over N, Q squared. And this expression I can write as 1/2 M minus N over N, M over N, P to the M over N, Q squared, which is, this is M over N minus 1 times M over N, over 2, P to the M over N, Q squared. What I'm doing is, in each successive term, I have a fraction times a new quantity. Like here, the new quantity is A, then B, then C, then D. And I see what the fractions are. The fractions, the denominators go 1n, 2n, 3n, 4n. The numerators go m, m minus 1, m minus 2n, m minus 3n. And we get some infinite series. So we get an infinite series that might stop. It might stop after finitely many terms, and it might not. But this is Newton's formula. So this is Newton's binomial theorem. Let me just, well, this is it right here. So Newton's binomial theorem, the way he wrote it down, and we'll change it to 1 plus x in a moment, but the way he wrote it down is P plus PQ to the M over N can be expanded in this way. The first term is p to the m over n, and each successive term involves a fraction, which we know, times something times q, and the something is the previous term. So the term previous to A is this. The term previous to B is this. The term previous to C is this, and so on. Right? So let me so the first term is A is P to the M over N. The second term B is this. If I factor out so we're expanding P plus Q. We're expanding P plus PQ to the M over N. In modern notation, you could factor out the P. This would be P to the M over N times 1 plus Q to the M over N. So essentially, what Newton is doing is expanding 1 plus Q to this fractional power. If you want to replace Q by X, that's okay. So where we have P plus PQ to the M over N, that's P to the M over N, 1 plus Q to the M over N. What does this expansion look like? The first term is P to the M over N times 1, let's say. The second term, M over N AQ, A was P to the M over N. If I factor that out, I get plus M over N times Q, right? That's what this is. What's the third term? I have M minus N over 2N. I could write that as M over N, let's see, what is B? This is B. Sorry, the third term. Am I doing this right? This is the first term. The second term, A is P to the M over N. So this is 1 plus M over N times Q. The next term, I have M minus N over 2N times B, which is M over N, times A, P to the M over N, times, I get a Q squared. Let's see. So I'm not sure this is clear. So let me just redo this, because this is Newton's binomial theorem. All right, so Newton's binomial theorem. Let me write it down again from the beginning and expand it. So Newton's binomial theorem says that P plus PQ to the M over N is P to the M over N. The next term is M over N AQ, where A is the previous term. The next term is M minus N over 2N BQ, where B is the previous term, plus M minus 2N over 3N CQ, where C is the previous term. The next term is M minus 3N over 4N DQ, where D is the previous term, and so on forever. So let me just try to write this in a simpler form. So A is the previous term. B is the previous term, m over n aq. But I know what a is. This is m over n p to the m over n q. C is the previous term. M minus 2n over 3n. Sorry. C is m minus n over 2n times bq, which is m minus n over 2n. And what is b? B is m over n, p to the m over n q, and so on. Let me simplify C a little bit. C is 1/2 m minus n minus n is m over n minus 1 times m over n p to the m over n q. Let me do one more term. D is the previous term. M minus 2n over 3n CQ, which is, let's see, m minus 2n over 3n, that's a third, m over n minus 2 times C, P times C, which is 1/2 m over n minus 1, m over n, P, the m over n q times q. So this is 1/2 times a third is a sixth, or I'll just write this 1 over 3 factorial. M over n minus 1, m over n minus 2, p to the m over n q squared. So I've just calculated the first 4 terms, A, B, C, D, in this expansion. So what do I get? I have P plus PQ to the m over n, which is P to the m over n times 1 plus Q to the m over n, is equal to A, P to the m over n, plus, P to the m over n, plus m over n AQ, so that's plus m over n, P to the m over n Q, plus m minus n over 2n B, which is m over n, P to the m over n Q times another Q makes that Q squared, plus this term, m minus 2n over 3n, CQ, this is C. C is 1/2 m over n minus 1, m over n, p to the m over n q, C is m over n 2n bq, which is this, that's right. B is m over n, p over q, q times q, this is q squared. So m over n, so this is p to the m over n, this is m over n aq, this is m minus n over 2n b q. This is b, m over n, p to the m over n q, times the q makes that q squared. Then I have m minus 2n over 3n, c, which is 1/2 m over n minus 1 over n, p to the m over n q squared, times the q makes that q cubed. And continue. So, and I can factor out, if I like, every term has this p to the m minus n, p to the m over n. Let me just cancel that to make it simpler. I get 1 plus q to the m over n equals 1 plus m over n q plus, this is 1/2 m over n minus 1 q squared, plus this is 1/2 times 1/3, I calculated that here, 1 over 3 factorial, m over n minus 1, m over n minus 2, q cubed, and so on. Okay. So this, just simplifying by canceling out the p to the m over n, this is Newton's binomial theorem. If I replace q by x, so it looks more modern, it says 1 plus x to the m over n is 1 plus m over nx plus 1/2 m over n minus 1 x squared plus 1 over 3 factorial m over n minus 1 m over n minus 2 x cubed and so forth. And I remind you that n factorial, n with an exclamation point, just means the product of all the positive integers up to n. So 4 factorial is 1 times 2 times 3 times 4, which is 24, for example. So that's what this is called, factorial. And factorial is the product of the positive integers up to n. These numbers get very big very fast. So this is the general form of Newton's binomial theorem. Now, I want to keep writing it down because this is something you have to know. I'll use x instead of p or q. 1 plus x to the m over n is 1 plus m over n x plus 1/2 m over n minus 1 x squared. Plus, of course, 2 is the same as 2 factorial. Because 2 factorial is 1 times 2, which is 2. Plus 1/3, 1/6, 1 over 3 factorial, m over n minus 1, m over n minus 2, x cubed. The next term would be 1 over 4 factorial, the exponent m over n minus 1, m over n minus 2, m over n minus 3, x to the 4th, and so forth. So let's look at a special case. Suppose I let m over n equal 2. So this should be an expansion for 1 plus x squared. So m over n is 2. So what do we get? We get 1 plus 2x plus 1 over 2 factorial, that's 1/2, m over n, which is 2, times 2 minus 1 x squared, plus 1 over 3 factorial, which is 1/6, m over n over n minus 1, n minus 2 minus 2x cubed. 4 factorial is 24, 1 over 24. 2, 2 minus 1, 2 minus 2, 2 minus 3, x to the fourth. And this keeps going on forever. And you might say, well, but 1 plus x squared is finite. It's not an infinite series. So what is this? This is 1 plus 2x. This is 1/2 times 2 times 1. A half times 2 is 1. 1 times 1. This is plus x squared. And all these other terms have a 0. This coefficient is 0. So all these other terms are 0. They disappear. So what Newton tells us, which we already knew, of course, is 1 plus x squared is 1 plus 2x plus x squared. Suppose we let m over n equal 3. What do we get for 1 plus x cubed? From Newton's formula, we get m over n is 3. This is 1 plus 3x plus 1/2 times 3 minus 1 x squared. Plus 1 over 3 factorial, that's 1/6. 3 minus 1, 3 minus 2 x cubed. Plus 1 over 4 factorial, 1 over 24. 3 minus 1, 3 minus 2, 3 minus 3, x to the fourth, and so on. So this is 1 plus 3x. This is 3 times 2 over 2 is 3x squared. This is 3 times 2 times 1 is 6 over 6 is 1, x cubed. And here, 3 minus 3 is 0. So the next term is 0. And every successive term is going to be 0. So I do recover exactly what we know. In fact, if we write, let's say, if I let, say, m over n be an integer, capital N, this formula tells us that 1 plus x to the n is 1 plus nx plus 1 over 2 factorial n times n minus 1 x squared plus 1 over 3 factorial n minus 1 n minus 2 x cubed plus 1 over 4 factorial n minus 1 n minus 2 n minus 3 x to the fourth and so forth. And we get that these binomial coefficients this is what you can deduce from this for the general formula. The binomial coefficient is going to be, or if you want the term x to the k, it'll be n minus 1, n minus 2, down to n minus k plus 1 over k factorial times x to the k. So the coefficient of x to the k in the binomial expansion of 1 plus x to the n is this, which is called the binomial coefficient. It's usually written as n k over k in parentheses. This is the binomial coefficient. So in general, the nth row of Pascal's triangle is going to be 1, n choose 1, n choose 2. That's the way this is written. n3, nk, n minus 1, 1. Where these numbers are given by this formula. So you can find the coefficients in the binomial theorem for positive integer exponents by using this formula for what are called the binomial coefficients. But this is just one very simple special case of Newton's binomial theorem. It's much more interesting to use Newton's binomial theorem when you have fractional or negative exponents. So the rule is always the same. This is Newton's binomial theorem, and let's apply it in a new case. Suppose I want to take one over 1 plus x cubed. I want to expand that into powers of positive powers of x. That is 1 plus x to the minus 3. So in Newton's formula, the exponent m over n is minus 3. So what do we get? This is 1 plus minus 3x plus 1/2 minus 3 minus 1 x squared plus 1/6 minus 3 minus 3 minus 1 minus 3 minus 2 x cubed and so on. This is 1 minus 3x minus 3 times minus 4 is plus 12 over 2 is 6. Minus 3 times minus 4 is plus 12 times over 6 is 2. Sorry, minus 12 over 6 is 2 times minus 5 is minus 10 x cubed. Let's see, what's the next term? When the term for x to the 4th would be 1 over 4 factorial. Four factorial, 1 times 2 times 3 times 4 is 24. Minus 3 minus 3 minus 1 is minus 4. Minus 3 minus 2 is minus 5. Minus 3 minus 3 is minus 6. X to the 4th. What is this? This is minus 4 times minus 6 is 24. Cancels this. Minus 3 minus 5 is plus 15. So 1 over 1 plus x cubed, when you expand it using Newton's binomial theorem, you get an expression like this. And this series goes on forever. It never stops. It's an infinite series. Right? Suppose you want to check. So you cross multiply. So 1 is 1 plus, should be 1 plus x cubed times 1 minus 3x plus 6x squared minus 10x cubed plus 15x to the 4th, so forth. Let's see. How can you check? Well, 1 plus x cubed, we already know how to expand that. That's 1 plus 3x squared plus x cubed times 1 minus 3x plus 6x squared minus 10x cubed plus 15x to the 4th, and so on. If I multiply this out, the constant term is 1 times 1. The coefficient of x, I get 3x minus 3x. For the x squared terms, I have 3x squared minus 3x times 3x minus 9x squared plus 6x squared times 1 plus 6x squared. See, what are the cubic terms? I have x cubed, I have 3x squared minus 3x minus 9x cubed, 3x times 6x squared plus 18x cubed, and 1 times minus 10 minus 10x cubed. See, what is this? This is, here I have 3 minus 3 is 0. Here I have 9 minus 9 is 0. Here I have 19 minus 19 is 0. All these terms so far, they cancel out. So just as a very rough check, looks like it's correct, right? That is, we have this binomial expansion of 1 plus x to a negative exponent. Right? Huh, interesting. Let's try another case. Suppose we want to expand by the binomial theorem the square root of 1 minus x. So x less than 1, certainly, but this is 1 minus x to the power of half. So this is 1 plus something. The something is minus x to the power of half. Okay. So this is like 1 plus q to the m over n, where q is minus x and m over n is a half. So let's try that. It's kind of interesting. So I'm interested in the square root of 1 minus x, which is 1 minus x to the power of half. So where was my binomial theorem? Where did it go? It disappeared. That's weird. My piece of paper literally just disappeared. Ew! Ew!
Bless you.
Thank you. Mhm. So let me just write down again the general form of this binomial theorem. So Newton's binomial theorem. So if you take 1 plus q to the m over n, this is 1 plus m over n times q plus 1/2 m over n minus 1 q squared which is 1 plus 1 over 3 factorial, or 6, m over n minus 1, m over n minus 2, q cubed, plus 1 over 4 factorial, m over n minus 1, over n minus 2, m over n minus 3, q to the 4th, and so on. And we're interested in expanding square root of 1 minus x, which is 1 minus x to the power of half. So in this case, q is minus x, m over n is a half. So this equals 1 plus m over n, a half, times minus x. Sorry, yeah, that's right, plus 1/2 m over n, a half, times a half minus 1, q squared, minus x squared, plus 1 over 6, a half minus 1, a half minus 2, minus x cubed, 1 over 4 factorial, which is 24, a half minus 1, a half minus 2, a half minus 3, times minus x to the 4th, and so forth. So this is 1 minus a half x. Here I have a half times minus a half. That's minus an eighth, minus x squared is plus x squared, minus 1/8 x squared. Here I have a sixth times a half times minus a half times minus 3 halves. So a half times minus a half times minus 3 halves. This is plus 3 over 8 . Let's see, let me just, something here doesn't look right. This is a half minus 1 is minus a half minus 2 is minus 3 halves. So this looks like 6 over 8, no, 3 over 8 times a sixth. So 3 over 6 is a half, so I get 1 over 16, and minus x cubed is minus x cubed, so minus 1/16 x cubed. Here I have, so this is minus 3/8. This is minus 3/8 times minus 5 halves, so this is 10 over 16, and 1 over 24 times that. So this is 5 over 12. And 12 times 16 is 144. So minus 144, no, 144 minus that's 12 times 16. 160, 192. Let me just double check. So I have a half minus a half minus a fourth minus 3/2. So 3/8, 24 over 16. Let me just do my arithmetic. Here I have 1 over 24 times 1/2 times -1/2. 1/2 minus 2 is -3/2. 1/2 minus 3 is -5/2. So this is equal to 3 times minus is minus. 3 times 5 is 15. 2 times 2 times 2 is 24 times 16. If I divide by 3, this is 5 over 8. So this is -5 over 128. So -5 over 128, x to the 4th, and so forth. Right? So that is, in fact, the book actually calculates one more term. The next term is -7 over 256, x to the 5th, and so forth. So this is Newton's binomial expansion for the square root of 1 minus x. Now, suppose you want to compute the square root of a number, like square root of 7. Nowadays, no one knows how to do this by hand. You take out your calculator, you take out your computer, and you get square root of 7. But Newton didn't have a computer, and to compute something like the square root of 7 to several decimal digits was hard. But using this binomial expansion, there's a way to get a very accurate approximation to the square root of 7. There's no exact formula. It's always an approximation if you write it as a decimal. So let's use the fact that 7 is 9 times 7 over 9. Right? That's true. Which is square root of 9 is 3. 3 times the square root of 7 over 9, which is 3 times the square root of 1 minus 2/9. So this is 3 times the square root of 1 minus x, where x is 2/9. So if I plug 2/9 into this formula, I can get a rational number that approximates this. Right? So what do I get? So square root of 7 is 3 times the square root of 1 minus 2 over 9. That's 3 times what? If I put 2 over 9 in for x, I get 1 minus 1/2 times 2 over 9 minus 1/8 times 2 over 9 squared minus 1/16, 2 over 9 cubed minus 5 over 128, 2 over 9 to the 4th minus 7 over 256, 2 over 9 to the 5th, and so on. And this is something I can calculate by hand. I can just compute these decimals, and what I get is 2.64576, which is pretty good. If you check on your computers, you'll see this is correct to these 5 or 6 significant digits. So all this comes from studying the binomial theorem. Yeah, pretty good. All right, well, I I hope when you signed up for this course, you didn't think that the history of mathematics was just going to be a lot of sort of fairy tales about exciting incidents in the personal lives of the great mathematicians. The point of the history of mathematics is to somehow see how mathematics actually developed over the centuries. And it used to be, and maybe still is the case, I'm not sure, that New York State requires that anyone who's going to teach mathematics in high school or middle school maybe has to take a course in the history of math. And one of the benefits from my point of view of this requirement is almost everything you're learning in this class, at least so far, fits into a middle school or high school math curriculum. It's not necessarily part of the curriculum, but if you know this and you're teaching, for example, as I started off by saying at the beginning of the class, if you're teaching how to solve a quadratic equation and you happen to know Cardano's formula, then just for general education, enlightenment, not that it's a requirement on a Regents exam or anything, you could tell your students that there is a formula for solving a cubic, and here it is. And everything we've done so far about prime numbers and triangles and such things, it all could fit into it. If you're the teacher, it enriches your knowledge when you're teaching your students, and that's a very good thing. So what I did today is actually technically rather difficult, I think, because if nothing else, you're seeing the binomial theorem in a new light, and you're seeing that even things that don't normally seem to be a binomial theorem problem, like expanding the square root of 1 minus x into power series. And you can do this with calculus, but the point of this is that you could do this, and Newton, in fact, invented calculus. Newton and Leibniz independently at roughly the same time invented calculus. But this is done without calculus. This is just these formal binomial series expansions. And there's a lot of mathematical meat on all of this. Okay. If there are no questions, that's probably more than enough for a day.
I have a quick question.
Yes, go ahead. Go ahead.
All right. You see the last answer that you highlighted in red?
This.
Yes. Can you when you get the -1/8, you also you also then multiply it by the negative x to the second power?
Yes. But negative x to the second power is plus x squared. So you end up with a minus sign.
Oh, okay. I see.
Yeah. Because when you take negative x to powers, negative x to an even power is positive, has a plus sign. Negative x to a negative power to an odd power has a minus sign. Right? It's just because negative times negative is positive.
Okay.
Right. Yeah. No, that's a good question. So somehow it looks like maybe the sign should alternate here, but it turns out they're all negative. Because whenever the coefficient is negative, the power of x is positive. And when the coefficient is positive, the power of x is negative. Or the power of x is odd, so you get a negative quantity. So that's why these all add up. These all come out to be negative numbers. And this is the kind of mathematics that you have to do really carefully. You have to keep staring at your work because they're minus signs and products of negatives, and you have to it's hard to keep it straight. And I'm actually glad whenever I make a mistake and you see me make a mistake, because first you realize everybody makes mistakes, and second, you see when you make a mistake, you just go back and do it again and try to avoid the mistake.
Does that also apply when we take tests? Because if
Yes,
we
when you make a mistake, go back and correct it.
All right.
Yeah. And that's why, normally I give a lot of partial credit. If it were like you get full credit if the answer is right and zero if the answer is wrong, exam grades would be a lot lower. Because, you make mistakes. And when you're doing it under the time pressure of an exam, you can't always go back and check your work enough times to realize you made a mistake, but that's just the way it is. Okay, that's it. Have a nice weekend and see you on Monday.
You doing the review on tomorrow at 7:30 or 7?
Yeah, I put this on. I had problem sessions like last night, tonight, and tomorrow at 7, and Friday afternoon at 4:30.
Okay, thank you.
Yeah. And like, usually it's not like an office hour. Like if I were on campus, I would be sitting in my office for an hour, and I have plenty, whatever. But on Zoom, it's not like an office hour. It's like a problem session. So so I'm on basically as long as people have questions. Or like last night, no one showed up. So after half an hour, I say, okay, I'll go have dinner. But yeah. But tonight and tomorrow night again at 7 and Friday at 4:30.
Thank you.
Okay. All right. Bye all.